Curl and divergence. Well, definition of curl. Suppose you have a vector field, let F be defined as P, Q, R, be a vector field in the space. Suppose the partial derivatives of P, Q, R exist as well. The partial derivative of P, Q, and R all exist. We're going to define the curl of F, curl of your vector field F, as the determinant of, before writing the determinant, the nabla operator cross multiplication with F, or as you remember, the nabla operator, partial derivative with respect to X, partial derivative with respect to Y, partial derivative with respect to Z, cross function F, which is P, Q, and R, which is nothing but the determinant of the following matrix. So here you have the determinant I, J, and K. This is your first row. The second row is the nabla operator. And then the last row are the components of your vector field, which can be written as, here you have I, partial derivative of R with respect to Y, minus the partial derivative of Q with respect to Z, minus J in the direction of Y-axis, partial derivative of R with respect to X, minus partial derivative of P with respect to Z, plus K times partial derivative of Q with respect to X, minus partial derivative of P with respect to Y. This guy is defined as the curl of your vector field. For example, suppose we have a vector field and I ask you to find the curl. Later on, you're going to see why we are using the curl. If vector field F is defined as xy, xyz, and negative y squared, then the curl of F is equal to the curl of F is equal to nabla cross F, which is just following the determinant. Here you have partial derivative with respect to X, with respect to Y, with respect to Z, and you're going to copy down the components of this well-behaved function. So here you have I times partial derivative with respect to Y, negative 2y, minus partial derivative with respect to Z, which is xy, minus J, and then you have partial derivative with respect to X, which is 0, minus partial derivative with respect to Z, which is 0, plus K. Here, partial derivative with respect to X is YZ, minus partial derivative with respect to Y is just X. So the curl of F is equal to a vector field negative 2y minus xy and 0. The second component is 0, and the last component is yz minus x. Just a quick theorem for you. If f is a function of 3 variables that has continuous second order partial derivatives, continuous second order partial derivatives, then for sure you can say that the curl of its gradient is equal to 0. Remember that to construct the curl, here you have the nabla cross this function. Remember, the gradient of a function is a vector field. So you're constructing these two. You are finding the cross product between the nabla operator with, here, this guy is partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z. It's not very difficult to see when you're forming your determinant that all components are equal to 0. And this 0 is a vector 0. It is equal to 0, 0, 0, or 0 bar or bolded 0. These are representing the vector 0.